Hey, Algebra 2. Today we're going to actually move our discussion on degrees into something that's called a radian. Okay, and why? So that's what we're talking about today. First of all, in our opening exercise, the first step in understanding why there is a need to change how angles of rotation are measured is to try to graph the sine function on a grid with the same horizontal and vertical scale. So we're going to struggle with this a little bit and come to the conclusion that either the horizontal scale or the vertical scale needs to change in order to be able to even see the graph of y equals sine x degrees. Okay, it's nearly impossible. So, first of all, let's construct the graph of y equals sine x, where x is the number of degrees of rotation. Back in lesson 5, we decided that the domain of the sine function is all real numbers, and the range is -1 to 1. So we're going to use our calculator to complete the table below with values rounded to 1 decimal place, and then graph the sine on axis below, which is on the next slide for us. Be sure that your calculator is in degree mode. So what you're going to do into your calculator is just hit the sine button and do sine of 0 and hit enter. Okay, sine of 30 and hit enter. And when you hit enter for sine of 30, you'll get quite a few decimal places. But just round it. Sorry. So I'm just going to type in sine 30, enter. And actually you get 0.5 exactly, because sine of 30 is 1/2. How about sine of 45? That's 0.707, which if you type in square root of 2, divide by 2, you get 0.707. So your calculator is calculating it for you rather than you going back to the unit circle to look at it. And then I went ahead and graphed on the x and y axis that was provided, and it was nearly impossible to even see. In fact, I'm pretty certain that this right here is too high because this is 10, and the highest point we saw was 1, and the lowest point was -1. So if this is 10, then certainly that point is too high, but I did the best I could. Looking at the table that you filled out, our smallest value is 0, our highest maximum value is 1, and our minimum value is -1. I said smallest value 0, I apologize. No, our smallest value is -1, our largest value is 1. And if our x and y axis, if our scale is not changed on one of those, you can't see the function, you can't see the graph, and that's not helpful, right? So what just happened with that graph? The graph is not usable. Let's go ahead and mess with our function y equals sine x. Oh goodness. Sorry, that's really funny. Sine x. Mess with our function to be able to use our graph better to see if we can actually see the periodic motion of that graph. Let's rewind back to what we did at the end of Module 1. We had a function y equals x squared, and we messed with that function a little bit to see how it would graph differently on an x and y axis, where if you look at the x and y axis, our scale is set. It goes -5 to 5, 0 and up, but everything is a unit of 1. It's not like we are changing the x-axis and not the y-axis, or changing the y-axis and not the x-axis. We just are going to mess with our function to change how our graph looks. So when we graphed, way back in Module 1, when we graphed y equals x squared, and when we graphed I just paused it for a second to fix my graph. If you notice, I had that one in incorrectly. In the previous, 5 seconds ago, I had 1/2 x squared, and I really needed that in parentheses. So I pushed pause and went ahead and fixed it. Okay, let's go back to what we were talking about. So back in Module 1 at the end of the unit, we graphed y equals x squared, and then we graphed y equals 1/2 x quantity squared. Okay, this graph was horizontally stretched by a factor of 2. So stretched by a factor of 2. And what we're actually doing is 1 over k x quantity squared. So we're actually stretching it by a factor of k. All right, that was a horizontal stretch by a factor of k. What horizontal scaling can we perform to compress the parabola y equals x squared to make the graph twice as narrow as the original graph? Because remember, like the previous slide, that graph is too far out. We need to compress it this way to make the up and down periodic a little more apparent. So if we did 1 over k, and that gave us a horizontal stretch, it sort of made everything come out. That is huge. I'll erase that in a second. 1 over k made everything go out, sort of pull out. Then if we just multiply by, y equals inside the quantity 2x squared, that compresses things a little bit. Let me actually change the color so we can talk about it. So y equals 2x quantity squared. That is right here. And it compresses everything a little bit. Right there. So I think that'll help with our problem up here. It'll take our unreadable graph and sort of compress it together so that we can read it. So right there, that would be our factor of k, and that will sort of compress everything a little bit. All right, let's try it. Oh, that's what we're doing. So we're going to redo everything by changing k for k greater than 1. All right, so set your calculator's viewing window to what's given, or I used Desmos. You can't use Desmos on any standardized tests though, so go ahead and practice in your calculator. Make sure your calculator is in degree mode and plot the following functions in the same window. Go ahead and try. Push pause. This is what I got. Okay, I used Desmos. I used Desmos so I could cut and paste it into this window and we could see it and talk about it together. So this was the first thing we talked about, which was sine x. And you'll see that's our red one, really unreadable. Okay, then I multiplied, I got k is 2. Okay, compressed it a little bit, got a little bit higher. K was 10. See, we're doing all right. Now we actually get into some meat and potatoes here, some interesting graphs. It actually is usable, right? When k was 50, now I can actually see the whole period. So from beginning to end. From there to there. That's our beginning to end. So with the green one, we can see it for the first time. And then sine 100, we can actually see a few of them. Like this would be that where it there is for k equals 100. And then over here was for k equals 50. So we actually have some graphs that are usable. Okay? We compressed everything by changing the coefficient in front of the x. I should make sure you guys know that even in my Desmos window, I had my x's set from 0 to 10 and my y's from negative 2.4 to 2.4. Okay, This viewing window was chosen because it has close to the same scale in the horizontal and vertical directions. In this viewing window, which of the 5 transform sine functions most clearly shows the behavior of the sine function? I would say y equals 50x or 100x would be valid answers there, because you could actually see an entire rotation. Describe the relationship between the steepness of graph y equals sine kx near the origin and the value of k. I would say as we increase k, as k got bigger, the steepness increased too. Since we can control the steepness of the graph y equals sine kx near the origin by changing the value of k, how steep might we want this graph to be? What is your favorite positive slope for a line through the origin? I sort of answered it for you. A slope of 1 is really nice because it's easy to count. Rise over run is 1 over 1. Super simple to work with. So let's see. Yeah, it would make sense to try to get the steepness of the origin to be the same as the diagonal line y equals x, because that's through the origin, because there's no y-intercept, or the y-intercept is 0, and it has a slope of 1. So that would be really a great way to compare things. So in the same viewing window, on your calculator, or Desmos, plot y equals x and y equals sine kx for some value of k. Experiment with your calculator to find the value of k so that the steepness of y equals sine kx matches the slope of the line y equals x near the origin. You may need to change your viewing window to determine the best value of k. I sort of found the answer for you. I graphed y equals sine 57x. It has nearly the same steepness as the diagonal line y equals x. If you see right here, you can't even discern between the two lines. Why is that? We're going to get into the why in a second, and that's sort of the strangeness about this lesson. Yeah, the value k equals 57 is special, okay? Okay, let's see if we can use this space to talk a little bit about the why. Let's talk a little bit about rotation and what we've learned about rotation. We have been working with a unit circle. I'm going to put it on the origin of a coordinate plane. So we've talked about a turn, and a turn is the entire, all the way around. So that would be one turn. I'm going to change that color. Okay, that would be one turn, right? So a rotation, we can also talk about it being a fraction of a turn. So for example, 1/4 of a turn is how many degrees? Right angle, 90 degrees, right? Half of a turn would be 180 degrees, or half the circle, right? That's a straight angle. But we really don't do that. We don't talk about turns. We talk about degrees, which is why everything we talked about with a turn, I turned into a degree, because we all know what a degree is. We divided a circle into 360 arcs of equal measurement. An arc being a piece of the circle. So if you have a circle, an arc is a piece of it, just a piece of the outside of the circle. We divided a circle into 360 pieces. Each piece, oops, each piece, or each arc, is 1 degree. So a turn is 360 arcs, or 360 degrees. Cool. Okay, I copied this straight out of the teacher's part of the curriculum because I thought it was really interesting. Who came up with our current system of using a 360-degree turn? Here it says, remember the ancient Babylonians. This is the half of the lesson that I skipped, so we really won't remember them, but we can talk about them now. Remember the ancient Babylonians who made all of those astronomical observations that led to the discovery of trigonometry? They are also the ones responsible for our system of measuring rotations and angles. It appears that the Babylonians subdivided the circle using the angle of an equilateral triangle as the basic unit. And if you remember, equilateral triangles have 60-degree angles. Since they used a base 60 number system, they divided each angle of the equilateral triangle into 60 smaller units, each with a measure of 1 degree, giving 360 degrees in a turn. So we've got 66 times. Inside the 60, they subdivided into 1 degree. Each degree is subdivided into 60 minutes, and each minute is subdivided into 60 seconds. This is just how you talk about the degrees inside of a circle. It has nothing to do with actual time, so don't get that confused. For our purposes now, using 360 degrees in a turn is cumbersome. Instead of basing our measurement system on an arbitrary number like 360, we will instead use a system in which the measures of angles and rotations are determined by the length of the corresponding arc of a unit circle. Again, we have a circle. If I have the center and a radius, this right here is the corresponding arc. And that's what we're talking about. So if this is my degree, we are going to relate it back to the arc. A circle is defined by a point and a radius. If we start with a circle of any radius and look at a sector of that circle with an arc length equal to the length of the radius, then the central angle of that sector is always the same size. We define a radian to be the measure of that central angle denoted by 1 radian, 1 rad. So every time we look at this, let's go circle by circle. I have radius of 1 centimeter, your arc length of 1 centimeter, so the angle measurement is 1 radian. If I have 2 centimeters, 2 centimeters, and 2 centimeters for the arc length, my degree measurement is 1 radian. And again, I have radius of our units and an arc length of our units. My degree measurement is 1 radian. So, a radian measures how far 1 radius will wrap around the circle. For any circle, it takes 2 pi, which is about 6.3, 2 times pi is 3.14 times 2. I should put that in the same order, shouldn't I? 2 times 3.14, which is about 6.3. So it takes 2 pi, or about 6.3 radius lengths, to wrap around the circumference. Now in this figure here, 6 radius lengths are shown around the circle, with roughly 0.3 radius lengths left over. So 1, 2, 3, 4, 5, 6, but we have that left over. But we can talk about it. Let's look at this we'll talk about that in a second, but let's look at this little exercise number 5. So use a protractor that measures angles and degrees to find the approximate degree measure for an angle with measure of 1 radian. Use one of the figures from the previous discussion. So I took a picture of one of the figures from the previous slide, and I just measured that this was 1 radius, and the measure of the degrees is from here to there, 57 degrees. So let me review that really quick. This is from one of the slides previously. This was R radius, and R units for the arc. Gives me a measure of 57 degrees. Okay, instead of emphasizing conversion formulas for switching between degrees and radians, we're going to talk about both systems as fractions of a turn. So a 60-degree rotation is 1/6 of a turn, right? Which is pi over 3 radians. Okay, pi radians is half of the full rotation, which we've already said is 2 pi, which is, well, pi radians is half a turn, which is 180 degrees. Okay, let's try these problems. Hold on a second. So for this first one, 45 degrees is actually 1/8 of a turn. I can take a circle, fourths is 90, eighths is 45. So 1/8 of a turn times 2 pi, which is a full turn, equals pi over 4 radians. 33 degrees, that's a little bit harder, so let's set up a fraction. I don't know why I did that. So that's the fraction of the turn. Let's multiply that by 2 pi. And a little bit messy, but that would be 11 over 60 pi radians. Notice how we keep the pi there. We don't multiply that pi out. We leave it as part of the answer. Okay, next, negative pi over 3. So that's really negative 1/6 of a turn because I'm going in the clockwise direction. I'm going to multiply that by 2 pi. Oh, this is already in radians. Erase that. I need to multiply it by degrees. Sorry about that. Trying to move too fast. Negative pi over 3 radians is negative 1/6 of a turn. I already had that written. Negative 1/6 of a turn. And a turn is 360. So that's negative 60 degrees. And then a little bit messier. So if this is radians, so we're at 19 pi over 17 of a turn. Oops. Looking at this though, it's really, I'm going more than a turn, right? So that would be 1 and 2/17. So if I look at my unit circle, I'm going 1 and 2/17. So this would be 1 turn, which is 180 degrees, and then 2/17 of a turn. So really we're trying to figure out what the whole degrees is. Okay? So we're actually going to multiply this one by 19 pi over 17 times a half, because we're at a half a turn, and then multiply that times 360. Oh, I don't know why I wrote 366. So 19 divided by 17 divided by 2 times 360 is 201.2 degrees. Cool? And I'm sorry, I made a mistake. That shouldn't be there. And this Should say radians. So sorry. All right, let's try another one. Okay, here we are looking at a whole table, so we're going to practice a little bit more. So we're going to perform the following conversions, and just, I would perform these on your own to give you just a little bit of practice, and then check your answer with what's written here. Okay, and star anything that may be confusing to you, and we will check it in class. Okay? Alright, now this last one. On your calculator, graph the functions y equals x and y equals sine times 180 over pi x. What do you notice near the origin? What is the decimal approximation to the constant 180 over pi to one decimal place? Explain how this relates to what we've done in exercise 4. So the graph right here is there, and what do you notice near the origin? I would say that the slopes are equal. It has a slope of 1. And then on a calculator, you can do 180 divided by pi, and it's about 57.3 degrees. Okay, so sine of 180 over pi x degrees is about equal, I should go like that, squiggly equal is about equal to sine of 57x degrees. Okay, this is what we were looking for in exercise 4, and I think I told you that in exercise 4. Okay, if degrees are changed to radians, then the expression sine of 180 over pi x, where x is measured in degrees, becomes just plain old sine x, where x is measured in radians. Then one period of the graph of y equals sine x on a grid with the same scale on the horizontal and vertical axis now looks like this. Okay, this is when we're now in radians, and we've got about the same scale as everything. So from this point forward, trigonometric functions will always be graphed using radians for measuring rotation instead of degrees. Because the discovery of that graph, besides the discovery that the graph of the sine function is much easier to create and use in radians, it turns out that radians make many calculations much easier in later work in mathematics. That's why we learn radians. So what did we learn? Okay, a radian is the measure of the central angle of a sector of a circle with arc length, the length of one radius length. So if this is the length of the radius, that's the length of the arc length. And then the central angle is called 1 radian. If there's no degree symbol, then radians is implied. So if there's no degree symbol in your problem, radians is implied. There are 2 pi radians to make a full turn, which is 360 degrees. From this point forward, all work will be done with radian measures exclusively for rotation. And that's really sort of our summary of the lesson. Cool? All right, last thing. Using this unit circle, let's go ahead and practice finding cosine of 7 pi over 6. Okay, here is 7 pi over 6. Cosine is the x term, so that's going to be negative square root of 3 over 2. Okay, now let's try to find sine of negative pi over 6. Negative pi over 6 is going to be this direction, the same distance as that direction, and sine is your y term, so that's going to be equal to negative 1/2. Okay, I think that's good practice. here's sort of your summary page that we just talked about in the previous page. And go ahead and review it, and I'll see you in class.